Check it, nerds. We're done. This is our last one. This is your last one for forensics, and it's also your last one for the HSC. So let's get into it. Today we're looking at emission spectra. I know this looks intimidating, but this might be our shortest forensics video yet. Probably won't be. We'll see. So this is going to be quite a bit. It's going to be revision from the previous topic, and we're going to talk about going from AAS to AES. So hang in there. So what are emission spectra? Basically, we know that electrons, they normally exist in a stable ground state, and these have very well-defined energy levels. And we know that if they absorb energy, because we heat it up or we apply electricity to it, they become excited, and they jump to a higher energy level. Now, that looks like what we see here. We have this gas here. It's letting all the lights going through. The electrons in the gas heat up, so they jump energy, and this means they have absorbed energy. So when they absorb energy, we get this emission absorption line there. Okay, so we've got an absorption line there. So when we take this source of energy away, the electrons they just chill out and they drop back down. Then they release a quanta, which is, well, sort of. They release energy, which is quantized, which means it's a discrete packet of energy. So it's on its own, it's not part of a spectrum. And it also has well-defined energy levels. And here it releases a line, an emission line. So we've got light source, gas there. We now take the light source away, so that will go black. But the gas will then release an emission line right there. Okay? So that's all pretty straightforward. The energy is released is proportional to the frequency, and inversely that means it's proportional to the wavelength for the physics students. You know what that means. So if the wavelength goes between the visible spectrum, which is 450 to 750 nanometers, we can detect it very easily. Very easily, actually. So let's have a look. What do we mean by specific absorption and specific emission? Okay, so since they have well-defined energy levels, it means that electrons can't possess energy that in between them. Okay, so if you've got level A and level B, it can't be A and a half. So electrons, they can also only absorb and emit the exact amount of energy that allows them to make a full jump. So there's defined levels. So there's here and there's here. They can't exist in between. So they'll absorb energy until they've got enough to go to there. And that's it. This makes them easily identifiable. So again, because it's inversely proportional to wavelength, atoms in the gas phase can only emit or absorb certain energies. And that's why we get a very clear line here and a very clear line here. And they are very clear. So basically, this allows us to do atomic emission spectroscopy, which looks like atomic absorption spectroscopy, but it's a bit simpler. So for example, since every single element has its own unique emission spectrum, we can identify elements present. If we know this, it's very, very easy. So for example, this is what it looks like. You're heating up your sample. It emits a light. The light goes through. You focus it with a lens. Your monochromator, which is what you use to separate out individual frequency wavelengths of light, or prism, bends the light, and you then shine it on a photographic plate, which is pretty sweet. And that gives us some cool pictures that look a bit like this, actually. Or the one on the first page, which was much better. Okay, so how is it done? You vaporize it and you place it in a flame or a carbon arc. Now, it's two carbon electrodes that are held together. An arc is something that allows electricity to arc across. So you vaporize it and you hit it with a flame, or the flame can give you, what's the word? The flame can give you false positives, basically. So if you vaporize it up and you hit it between two carbon plates, two carbon electrodes, and you put large voltage between the two, then the electrodes get excited, sorry, the electrons get excited, go up and drop and emit energy. We then focus that radiation with a lens, which then goes through a monochromator, probably a couple, and these prisms separate it into its component wavelengths. And we can detect it by three ways. One, photographic plate or film. Looks like that. The spectrograph, spectrum gives you the spectrum, and it's a photo. It's a picture. You can use a photomultiplier, and this is a spectrometer. So a spectrometer it'll give you a graph, okay? It'll give you a graph, and that's the one that you use in AAS. A photographic plate gives you a spectrograph, so spectrometer, spectrograph. The other one you can use is a spectroscope. So a spectroscope is one thing you look through. You might want to tabulate these three so you know them. Emission spectrum can be observed directly. You just look at it through an eyepiece, and it's pretty sweet. Now we can use it for quantitative analysis, and that's cool. But AAS is much more accurate for that. So you wouldn't. You just wouldn't use it. But what you can do is you can AES compared to AAS. So AAS, you can only look at one thing. AES, you can look at as many as you want. You can have all of your different mixtures in there at once. You don't need to separate them. If you can vaporize them and get it through the carbon arc, you can see all of the different elements in there because they're all unique. So what are the uses? You want to be able to identify elements through it. So it's actually becoming more and more useful as it's become faster and more sensitive. But how would you use it in forensic chemistry? Lead poisoning. Basically, you could just detect elements that are in samples of blood or tissue. You can work out where paint comes from by comparing the composition of the paint at different locations, or composition of paint on a body from that of a car that you think might have been involved in a hit and run. You can determine the origin of small pieces of glass. So now we're going back to our, I think, second or first video. Small pieces of glass or alloys. And this is really, especially glass, because glass is highly variable. So you can compare it with those from the likely places. You can determine the origin of a soil sample based on the minerals that are in the soil. You can also identify forgeries. Paints of different times, or paints used by artists, are going to be different than those used by forgers. There are limitations, like everything else. It's not perfect, and this is the bit where we have to choose what we're using. So let's have a look at the limitations. It's less accurate than AAS for quantitative analysis. It is almost useless in analyzing organic compounds, as there are so many different organic compounds that just have hydrogen, oxygen, and carbon. You can use it for identifying small organic compounds, like your vinyl chloride, because they have known... no, not vinyl chloride, my bad. You can't do that. Leave it alone for organic compounds. The biggest disadvantage, though, is that it is, again, a destructive analysis. You need to vaporize it. If you're vaporizing it, you can't repeat it if the sample is tiny, and that's all you've got. However, it's getting better. They now use plasma to excite electrons, and you can excite more electrons compared to carbon arc, which, if you're talking about very, very large atoms, you can get a much more detailed map. So you might struggle to tell the difference between, say, uranium and plutonium. But if you, which have been used to poison people in recent years, or plutonium has. So if you have the right set, if you can heat it up to a much higher temperature, you can excite all of the electrons. And that's it. I hope you've enjoyed forensics. It's been good having you, and we'll see you in class.